In this video, we'll be looking at our half-angle identities. Our half-angle identities are these three right here in the middle of our formula sheet. They come after the double identities, but technically before our power-reducing identities. We can conclude where they come from or how they are developed by looking specifically at our double angle identities up here. Once again, just very much like we did our power-reducing identities, we can prove these half-angle identities by utilizing our double angle identity for the cosine of 2x. This one takes a little bit more of a finesse to it and a skill that we might not have used in the past. So let's go through that real quick. If I start off with the cosine of 2x equaling to 1 minus the sine squared of x, we can solve this equation for sine of x. We can take those steps that we did in the power-reducing identities video by adding this across, subtracting this across, giving me sine squared of x is equal to 1 minus cosine of 2x. We can also then square root both sides. This will provide us with sine of x is equal to plus or minus the square root of 1 minus, there's a 2 missing here, a 2 missing here, so this ends up being divided by 2 in the grand scheme of the problem, and then square rooted. So I'm going to have a division by 2 here, and the square root should extend all the way down underneath there. So 1 minus the cosine of 2x, all divided by 2. Well, at this point, you might look at your formula sheet and say, but that's not a half-angle identity. And you're correct that this is sine of x over 2 equals to plus or minus the square root of 1 minus cosine of x, all divided by 2. But you'll also notice that technically this x and this 2x have the same relationship as this x over 2 and this x. So if instead of utilizing x, I decided to let x equal, say, alpha over 2, that means that my 2x is equal to simply alpha, and that this formula ends up becoming the sine of alpha over 2 equals to plus or minus the square root of 1 minus the cosine of just alpha, all divided by 2. Now, you'll notice if instead of using x's I used alphas, that this identity now is the same as this identity here. So the trick here is that we can do our basic algebraic manipulations, but then there's also a substitution of an angle in terms of variables for us to better reference the half-angle identities and how to utilize them. What's also important to note is during these half-angle identities, each of them have a plus or minus except for the tangent. We have to make sure we're really careful about selecting where x over 2 is landing. Again, the sign is determined by which quadrant x over 2 lies in. So we have to remember that, again, all students take calculus mnemonic devices in terms of all trig functions are positive in the first quadrant, sine is positive with its reciprocal cosecant in the second quadrant, and so on and so forth. So depending on what x over 2 ends up being will tell us whether or not this thing overall has to be a positive or a negative number. For our first couple of examples, we're going to go ahead and take a look at the cosine of 210 degrees equals to a negative radical 3 over 2 in order to find what is the cosine of 105 degrees. It's important to note that there are very few expectations, or the chance of me providing or somebody providing you this piece of information is slim to none. They'll provide this or ask you to find this, and you'll have to know where you're going to pull that information from. There might be a couple of different ways to do this problem, in which case you might end up not using a double angle or a half angle rule, but it's important for us to know that that skill is still there. So at this moment, I know that the cosine of 105 degrees is really the same thing as the cosine of 210 degrees divided by 2. If I make that note, if I can at least register that, and I know that 210 degrees is on the unit circle when 105 isn't, I can go ahead, and again, I'd pull that cosine of 210 degrees here from the unit circle and get that piece of information for my use later. But in this location right here, the cosine of 210 degrees divided by 2 is a cosine of 105. The cosine of 105 is going to land over in this quadrant here, meaning that, again, all students, sine is positive, which means that cosine has to be negative. That's what we're going to go ahead and identify in that second quadrant, is that this value is supposed to be a negative number. And this is equal to this, which is equal to plus or minus, based on our identity sheet, the square root of 1 plus cosine of x divided by 2. So the square root of 1 plus the cosine of x divided by 2, such that x is 210. Be very careful when you're using these formulas. The x is going to be divided by 2 in our first piece and in cosine all on its own in the actual formula. So I'm going to go ahead and say it's plus or minus, but based on this detail here, and our 105 angle, the original cosine that we're being asked to find, is in the second quadrant. I know it has to be a negative number of the square root of 1 plus the cosine of 210 degrees, because the formula of this and this location are supposed to match up, divided by 2. In which case I get negative square root of 1 plus a negative radical 3 over 2, all divided by 2. I can distribute that division and simplify a little bit. Square root of 1/2 minus radical 3 over 4. If I wanted to, I could simplify that just a step further and give myself a negative square root of 2 minus radical 3, all divided by 4. In which case I could pull the 1/2 out, giving me a negative finality of a square root of 2 minus radical 3, all divided by 2. But there's not much more going any further with this can do. Again, we can't pull a radical outside of a radical, not to mention the fact that there's a plus or minus here, which we can't combine those terms smoothly. The only thing that we can really simplify is that 4 that's inside the original radical, and then that 4 can simplify down to 2 being outside the radical. Therefore, we have simplified what is the cosine of 105 degrees by using a half angle identity into this detail here.